Scientists have lied for half a century. The James Webb Space Telescope, aimed at absolute darkness. In that void, hides something that could rewrite every textbook. For decades, astronomy believed the universe is vast but measurable. 14 billion light-years in every direction, scattered with hundreds of billions of galaxies. This picture was grand, ordered and certain. Welcome to episode 377 of Kuiken Universe, Webb. The telescope turns to a dark zone that seems empty. That darkness was never truly empty. 93 billion light-years. This is the reality of the observable universe. Webb sees countless stars, even where theory forbids them to exist. Galaxies 300 million years after the Big Bang had already grown into adult forms. Black hole growth rates silence the laws of physics. But the scariest discovery isn't how far Webb sees. Webb proved that we can never reach most of the universe. To understand Webb's true discovery, one must first discard an instinctive illusion. The world the human eye sees is immediate. The moon is 1.3 light seconds away. The sun is 8 light minutes away. But staring at the night sky still isn't watching the present. One is flipping through an archive written over 13.8 billion years. Light speed is fixed at 300,000 kilometers per second. Circling Earth takes just 0.13 seconds. However, this fastest messenger carries a fatal delay. Look at a house 1.6 kilometers away. That house belongs to a few microseconds ago. Look at the moon, that's an after image from 1 second ago. Look at the sun, that light left the surface 8 minutes ago. When the gaze leaps beyond the Milky Way, the delay grows from seconds and minutes into units of years. The night sky is not a snapshot, it is a graveyard. Every photon is a message from billions of years ago. The universe doesn't preserve letters as they were. Space is expanding. As light travels through stretched space, its wavelength is forcibly elongated. Blue light turns red. Eventually, light falls into the infrared band. Redshift is not a color game. Redshift is the timestamp carved by the universe. For the past half-century, Hubble struggled to dig invisible light bands. Hubble saw galaxy collisions, saw stellar nurseries, saw the cosmic web skeleton. But as Hubble tried to peer deeper into time, the images began to fade out. Those ancient galaxies didn't disappear. It's just that the light they emit has stretched beyond what the human eye and Hubble's lenses could ever catch. Webb was born specifically to retrieve those missing letters. Webb's primary mirror is 6.4 meters wide. Its surface is covered in micron-level gold plating. Gold's efficiency in reflecting infrared is unmatched by any other metal. Webb is not in Earth's orbit. The satellite is at the second Lagrange point, 1.5 million kilometers away, staying stationary. At that position, the sun, Earth, and Moon's stray interference and heat are all blocked by the sun's shield. The mirror's temperature must be kept below -233 degrees Celsius. Infrared detection captures heat. If the telescope has even a hint of warmth, it drowns out faint signals from 13 billion years ago. Webb must become quiet enough to hear the universe's whispers. Staring at a completely pitch-black pixel, Webb is not searching. He is waiting. Waiting for those photons stretched to near invisibility by expansion, arriving at the mirror one by one. Sometimes exposing for 100 hours, just to collect a few hundred photons. And the images brought by those photons sent chills down the spine of astronomy. The early universe shouldn't be so bright. The standard model's cosmic dawn was dim, slow, and cautious. The first stars ignited sporadically. The first galaxies were fragile and sparse, taking billions of years to reach normal size. What Webb saw was a carnival. 300 million years after the Big Bang, less than 3% of the universe's current age. Compressing 13.8 billion years into a one-year calendar, galaxies appeared on January 2nd. Just after New Year's Day, cities were already built. Webb's spectrometer detected carbon, oxygen, and nitrogen. These elements did not exist at the moment of the universe's birth. They must be forged in stellar cores. Must wait for the first stars to burn out, and spread via supernova explosions. When Webb caught heavy element signals, it meant an earlier stellar era was already over, completing a full cycle. The universe didn't start slowly at all. It rushed directly into the complex phase. Those galaxies were so bright, they must have contained massive amounts of stars. Astronomers calculated the total luminosity early galaxies should have. Theory versus observation differed by 2 times, 5 times, or even 10 times. This gap isn't a measurement error. It's a systemic breakdown. Researchers performed every check. Suspected dust obscuration. Suspected gravitational lensing amplification. Suspected black hole jets boosted brightness. After every calibration, the mass of early galaxies still exceeded limits. They were privately called universe breakers. The existence of these bodies questions the very foundations of cosmology. According to known physics, there wasn't time in such a short window to pile up such massive groups of stars. unless our understanding of the early universe has been wrong from the start. A thornier problem lies in galactic centers. Webb discovered supermassive black holes living in a universe less than 500 million years old. Some are millions, even billions of times the mass of the Sun. The traditional path: massive stars collapse. Seed black holes are about dozens of solar masses, then grow slowly by devouring surrounding matter. The problem is accretion efficiency. Matter falling in releases massive radiation. Radiation pressure pushes subsequent matter away. Even under ideal conditions, growing into a billion solar mass black hole requires time far beyond what the early universe allowed. However, Webb time and time again, at positions disallowed by the timeline, found behemoths that shouldn't exist. Either first stars grew to thousands of solar masses before collapsing into giant seeds, or gas clouds collapsed directly into black holes, skipping the star phase. Or the early universe experienced an unimaginable dense merger. 3 possibilities. All 3 point to unknown physics. Webb also did something else unsettling. He counted how many galaxies are in the universe. Hubble's deepest images revealed nearly 10,000 galaxies. In a dark area just 1% the size of a fingernail. Astronomers then estimated the observable universe has hundreds of billions of galaxies. That number was already incomprehensibly large. Webb looked at the same patch of sky. Hubble saw black gaps. Webb saw faint light. Smudges Hubble barely identified, Webb resolved into spiral arms and bulbs. Those galaxies never disappeared, their light just shifted to infrared, slipping past Hubble's lens edges. Webb caught them, and they are stunning. Webb exposed for hundreds of hours, stacking over 10,000 independent exposures. The final image is packed with nearly 800,000 galaxies. 800,000 galaxies, in a sky area the size of 3 full moons. Scale bars completely fail. If Hubble's ultra-deep field is on A4 paper, Webb's field needs a 4m×4m sheet to restore the same detail. A whole wall covered in points of light. Every point isn't a star, it's a galaxy. Each contains millions to trillions of stars. Countless planetary systems reside within. Complex chemical elements cycle in the interstellar medium. Dust, organic molecules, and heavy elements extracted from star deaths. The universe is not sparse islands. Scattered darkness is densely filled. Layered scales of Webb's navigation. He measured the distance of every light point. Mass, star formation rates, approximate age. From cosmic dawn to today, galaxy evolution is tracked coherently for the first time. The results reveal a deeper pattern. Galaxies are not drifting randomly. They are lining up. On the largest scale, the universe appears like a spider web. Filaments millions of light-years long crisscross. Junctions gather thousands of galaxies. Areas between filaments are barren voids. Webb reveals the web's weaving speed is far faster than expected. When the universe was only a few billion years old, fibrous structures tens of millions of light-years long had already taken shape. Some structures challenge formation theory. Astronomers named a new galaxy chain the Cosmic Vine. At least 20 galaxies tidally linked, stretching 13 million light-years. More bizarrely, several of the largest members have already stopped making stars. Gas exhausted. Star formation extinguished. In an era where most galaxies were still in their infancy, these galaxies have already entered old age. Environment dictates destiny. Violent interactions in crowded spaces can wildly accelerate a galaxy's life cycle. Webb compiles the deepest, most complete galaxy group catalog to date. Over 1,600 groups and protoclusters, covering a 12 billion year span. Early groups were chaotic, their galaxy shapes distorted, star formation out of control. Late groups are orderly. Galaxies are smooth and round. The rate of new bursts is steadily declining. Gravity is gradually taming the flows. This continuous evolution seeks to refute the past. It is impossible to obtain. Yet the other half of the universe is defined by nothingness. The voids between filaments span hundreds of millions of light-years. Stand at the center and look in any direction. There is nothing for billions of light-years. In the same cosmic growth map, dense clusters and pitch-black voids sit side by side. The universe is both crowded and desolate. Chaotic yet barren. Complete in structure, yet with vast empty spaces. If Webb's observations are representative, confirmed by independent observations in multiple directions, then the total number of galaxies in the observable universe is not hundreds of billions, but trillions. Not a single previously known galaxy was found. Another 10 are lurking. Beyond the detection limits of previous telescopes. More galaxies mean more stars. More stars mean more planets. More planets mean more soil for complexity to grow. The universe is not just expanding in scale, it is expanding in the dimension of possibility. But even these astronomical figures are limited to the observable portion. Beyond the boundary, space continues to stretch, structure continues to form, and the trail clearly shows one thing: the visible universe is far more crowded than imagined. So, what is the scale of the parts that remain forever invisible? Intuition traps most people in an illusion. The universe is 13.8 billion years old. The speed of light is constant. Inference: visible celestial bodies should be 13.8 billion light-years away. Intuition was wrong. The observable universe's radius is not 13.8 billion light-years. It is 46.5 billion light-years. The total diameter is 93 billion light-years. This is not artistic imagination. It is a direct measurement of universal expansion. No galaxy is flying through space faster than light. The laws of physics haven't been broken. The universe used a craftier way to break the limit. Space itself is stretching. Imagine ink dots on a balloon. As it inflates, every dot moves away from the others. No single dot is the center of expansion. No dot drifts by its own power. The skin expands, and the dots follow. The same applies to the universe. When a distant galaxy emitted the light captured by Webb today, that galaxy was much closer than it is now. Over tens of billions of years, as light raced toward Earth, space continued to stretch. By the time the light reached the mirror, the galaxy that emitted it had been pushed over 40 billion light-years away. Light didn't just cross a fixed distance, it crossed a distance that was growing. Early expansion was slow, so photons moved forward steadily. Later, expansion accelerated, and space stretched faster and faster. Some photons set out early enough to reach the end before expansion spiraled out of control. Others are forever trapped on the way. This creates a boundary, the cosmic horizon. The horizon is not an edge where space ends. It is a causal barrier, the limit of cause and effect. Given the universe's age and expansion, light from beyond the horizon will never reach Earth. Not for lack of time, but because space expands faster than light. Space does not end at the horizon. Evidence is scattered across the sky. Galaxy distribution doesn't thin out toward an edge. The cosmic microwave background is almost perfectly uniform. If space had a hard cut-off at our vision's limit, this smoothness would be inconceivable. The universe extends far beyond the visible part, but it does so in a way that keeps the vast majority permanently hidden. Galaxies 46.5 billion light-years away are still burning, closing in on death. The full history of the universe plays out in regions we can never touch. No signal will ever reach Earth. It has nothing to do with technology. The structure of space-time prevents communication. What's more disturbing is that the horizon is not fixed. As time goes by, the observable universe slowly expands. More ancient light gets a chance to arrive. The horizon creeps outward. Meanwhile, dark energy drives expansion faster. The speed of space stretching is increasing. The two effects are in a tug of war. As a result, some objects briefly enter our view, only to be thrown out forever. Galaxies visible today might not be there tomorrow. The light they emit will continue to stretch, redshifting into bands that instruments cannot resolve. From a human perspective, they will freeze into a historical image, slowly fading until they vanish completely. This is not just theoretical speculation. It is a direct consequence of the expansion rate. In the next 100 to 150 billion years, except for our local group, all galaxies will cross the cosmic horizon. By then, when astronomers look at the sky, they will only see a small cluster of nearby galaxies, suspended in endless darkness. The cosmic background radiation will dissipate. The web of distant galaxies will disappear. All evidence of expansion will be erased. Future generations will never know that trillions of galaxies once existed. The observable universe is not the whole universe. It is just a slice from Earth's position that we happen to be able to see right now. If we move to another galaxy, the observable universe would reconfigure. Strange galaxies would enter the view, and old boundaries would sink below the horizon. Every point in space defines its own observable universe. This leads to a counterintuitive reality. Two galaxies might both be visible from Earth, yet cannot see each other. They sit on opposite sides of our horizon. Light cannot travel from one to the other. From their perspective, Earth itself is already beyond the horizon. There is no privileged observation point. There is no center. No coordinates can govern the entire universe. Every observer, no matter where they are, sits at the center of their own causal bubble. This is the core of Webb's revolution. When Webb detects extreme redshift objects, it isn't just showing ancient objects. It is showing the limits of causal connection. Those galaxies are no longer where the light began. Their current state and subsequent closure, their evolution, and even their destruction, are forever sealed away from Earth. Information is still trekking through space, diluted by expansion. Most of it is stretched and will never arrive. What Webb sees is not what is. What Webb sees is what was. And even this is incomplete. Beyond the horizon, the unobservable universe unfolds. Filled with equally rich and complex clusters, filament structures, and dark matter clouds. Some models suggest an infinite universe. Others claim it is finite, but so large as to be meaningless. Either way, the observable part is almost certainly just a tiny fragment. James Webb hasn't revealed the universe's edge. It has revealed a much harder truth: there is no reachable edge at all. If most of the universe is hidden by expansion, if reality extends infinitely beyond the horizon, then something must exist to drive that accelerated expansion. To understand that thing, we must face the universe's most dominant and mysterious component. The 20th century expansion story was simple. Matter scattered after the Big Bang, and gravity tried to pull it all back. Astronomers debated if it would expand forever or eventually collapse. The premise was the same: gravity was in control. By the late 1990s, that premise died. Astronomers studying Type Ia supernovae found an anomaly. Those explosions have very stable brightness. They are reliable cosmic yardsticks. By comparing observed and theoretical brightness, and combining them with recession speeds, the history of expansion had nowhere to hide. The data pointed to the opposite of expectations. The universe wasn't slowing down. It was accelerating. Distant galaxies were further away than gravity models predicted. Something is pushing space apart, not just expanding, but accelerating it. The push is getting faster. The early patterns are becoming clearer. Expansion has accelerated for billions of years. Physics was forced to introduce a new component: dark energy, invisible and untouchable. It doesn't emit or absorb radiation. It has no stellar properties. Yet it is everywhere. Evidence comes from its effect on expansion. That effect is overwhelming. Current measurements show dark energy makes up about 68% of the total. Normal matter, including all stars and planets, gas, and life, makes up less than 5%. Dark matter fills the rest. The visible universe, that familiar and solid-feeling universe, is just a byproduct of reality. The most unsettling trait of dark energy is that it doesn't dilute as space grows. Matter density drops as volume increases, falling in inverse proportion. Radiation decays even faster. But dark energy density remains constant. If space doubles, the total dark energy doubles too. More space creates more dark energy. More energy drives faster expansion. Faster expansion creates more space. A feedback loop spanning billions of years. The cosmic balance of power has shifted. Early on, matter led gravity to carve galaxies. Stars were the kings of the universe. But as matter was diluted, dark energy quietly took over. 5.1 billion years ago, dark energy became the dominant factor. Webb doesn't directly detect dark energy, but everything Webb sees. The extreme stretching of ancient light, the vast size of the observable universe. Galaxies are accelerating away. The fingerprint of this invisible force. Without dark energy, the universe would be much smaller. The cosmos would face collapse. Today's vast visible regions would never have entered our view. Dark energy doesn't just shape the present, it determines the future. If energy levels remain constant, current observations support eternal expansion. Galaxy clusters are held by gravity, but everything else will gradually fade. In 1 trillion years, astronomers will see a lonely universe. Nearby stars are everywhere, but beyond them, there is nothing. The universe remains, but it will look almost deserted. But this landscape is split by cosmology's deepest crack. To measure the current expansion rate, scientists can't find a single answer. They found two. The first method peers into the ancient past, via the cosmic microwave background. The afterglow from after the Big Bang helps reconstruct expansion history. The result, about 67 kilometers per second per megaparsec. The second method targets our neighbors, measuring supernovae and Cepheids. By comparing galactic recession speeds, the result is about 73 kilometers per second per MPC. Both measurements are precise, both have been verified repeatedly, and both have been strictly reviewed. Yet, they do not match. This rift is called the Hubble tension. It's the deepest crack in cosmology. The Webb telescope was expected to end the debate with more precise measurements. Webb provided clearer data, confirming a higher local expansion rate. The tension hasn't disappeared, it has been sharpened. Cosmology is in a dangerous stalemate. Either the measurements are wrong, or our core assumptions are. Either way, the model lacks something. Perhaps dark energy isn't constant. If its strength evolves over time, the expansion rate would change. Current models don't capture this. Another possibility, unknown physics affects light travel, distorting our measurements. Or perhaps early universe behavior established expansion traits that evolved into unpredictable forms. Each possibility is devastating. The expansion rate dictates cosmic age and our ultimate fate. If it continues unchecked for decades, our conclusions will need mass revision. Extreme scenarios aren't ruled out, like dark energy increasing over time. Expansion might overpower gravity, even on small scales. Galaxy clusters will be torn apart. Galaxies themselves will disintegrate. Stellar systems, planets, molecules, even atoms will be shredded in a big rip. Data doesn't favor this end yet, but uncertainty remains. Measuring dark energy is difficult. It is unsettling. Tiny changes have massive consequences. The facts are established. Dark energy dominates the universe. Dark energy stretches space. Dark energy pushes most of reality out of our sight. It dictates what can be seen. Dark energy is the only reason the universe is so vast. It is the ultimate reason most things stay hidden forever. Yet dark energy alone can't explain the universe Webb has revealed. While it tears space apart, there must be a counterforce. A force must counteract expansion to allow galactic structures to grow, rather than diffusing into fog. That force is also invisible, equally mysterious, and equally vital. To understand the universe, and how it stays together, we must look at every galaxy, every cluster of stars, and the cosmic web's fibers. If dark energy rules expansion, dark matter rules cohesion. Without dark matter, the universe Webb reveals would not exist at all. Galaxies could not form, galaxy groups would fly apart, and giant cosmic structures would remain a uniform fog. Dark matter emits no light, absorbs no radiation, and sends no detectable waves. It outweighs visible matter 5 to 1. 85% of cosmic matter is dark matter. Its only trace is gravity. Every star, planet, and nebula, and every galaxy is built within an invisible frame. The first clue appeared a century ago. Galactic behavior seemed absurd. Outer stars moved far too fast. Gravity from visible matter should have flung them into space. Yet, they were held in place, as if every galaxy was embedded in an invisible halo. That mass is dark matter. Evidence continued to mount. Clusters showed the same symptoms. Entire groups of galaxies moved at speeds far beyond visible gravity's reach. Gravitational lensing revealed distortions beyond visible limits. The conclusion was unavoidable: most cosmic matter is transparent. Quantity isn't the only secret. It's about how dark matter behaves. Unlike normal matter, dark matter doesn't collide. It doesn't lose energy to radiation. It moves through space frictionlessly. This let it clump together early. Right after the Big Bang, tiny density ripples appeared. Dark matter responded first. While normal matter was too hot, dark matter quietly gathered. Forming giant invisible halos, they became cosmic scaffolding. After the universe cooled, normal matter fell into these wells. Gas compressed and ignited. Stars began to shine. Galaxy formation wasn't random, it followed where dark matter led. The visible universe mirrors an ancient invisible blueprint. This carved reality's features. On the scale of the cosmic web, matter forms massive filaments. Clusters meet at intersections, surrounded by vast, empty voids. This structure is no accident, it's the result of gravity acting on dark matter over eons. The Webb telescope brings this into focus. By measuring galaxy distances, astronomers mapped cosmic matter. The pattern is undeniable. Galaxies line up along filaments, clustering at the junctions, while the voids remain empty. The universe grows on this frame. Webb pierces dust to find galaxies that were previously hidden. This fills the cosmic web's gaps, revealing an earlier structure. Billions of years ago, the filament system was ready. Matter flows toward clusters. This flow is quite literal. Observations show gas channeled along dark matter filaments, like traffic on a highway. Galaxies grow internally, but also by drawing in fuel along these invisible routes. The Milky Way does the same. Our solar system's home sits on a filament of dark matter. At this scale, motion is guided. For decades, we relied on indirect evidence. This year brought a breakthrough. Using gravitational lensing, scientists measured light passing through predicted filament zones. The faint deflections were subtle but consistent. Mass exists without visible light. Dark matter isn't just in clusters, it stretches across space. It weaves the universe together. This turns the web into reality. The universe isn't a loose collection, but an interconnected network. Network nodes are galaxy clusters. These are massive bound structures. A cluster holds thousands of galaxies, superheated gas, and immense dark matter. They anchor the flow of matter. Galaxies entering clusters change. In these dense environments, gas is stripped away, halting star formation. Webb captures this transition. The images show the evidence of environmental transformation. The cosmic web is active. Yet, dark matter remains a mystery. No one knows what it is. It could be an unknown particle. It could involve new physics. Decades of lab experiments have yet to detect it directly. But its existence is undeniable. Every galactic orbital flaw, every gravitational map, and every large structure points to the same conclusion. Dark matter is the cosmic foundation. It is the invisible architect of everything we see. The search continues to unveil this mystery. The final truth awaits. Its existence is undeniable. Every galactic rotation defect, every gravitational lens map, and every large-scale formation leads to one conclusion. From the equations, dark matter observations show the universe shouldn't exist. Microwaves don't solve the dark matter puzzle. Webb reinforces dark matter's core role. By revealing how fast early structures formed, Webb proves visible matter alone couldn't do it. Dark matter provides a gravitational head start, allowing assembly just a billion years after the Big Bang. New models also explain the universe's current look. Vast voids of movement. Dense clusters of abundance. Fibrous bridges connecting the two. When dark matter dominates gravity, all of this emerges naturally. Yet this invisible skeleton operates in a universe torn by dark matter. Dark matter builds the structure. Dark energy stretches space. The universe is locked in a duel of invisible forces. Small-scale gravity wins. Galaxies are born and grow rapidly. Large-scale dark energy takes the lead, pushing galaxies apart. Regions of space pushed beyond the world. Webb shows the universe is larger than expected. It is more orderly than expected. More interconnected than expected. More reliant on invisible forces than expected. What the eye can see. Stars and galaxies. Nebulae are just deeper structures. An illuminated surface. That structural layer is invisible. That structural layer sustains reality. When pulling back far enough to gaze at this structure as a whole, another realization is unavoidable. This interconnected universe is still just like Earth. Within the observable slice of space-time. Beyond, the universe is shaped by the same invisible forces. In worlds humans can never cross. Unfolding endless chapters. When light began its journey 13.8 billion years ago, Earth was not yet born. The sun was not yet lit. The Milky Way, from gas and dark matter principles, assembled itself. Ocean life. History of human civilization. Every chapter written during the photon's trek. When Webb finally captures those photons, humans aren't watching events happening now. Humans are watching what happened long ago. Preserved during transit. Moments that never repeat the same way. This is why astronomers say, Webb doesn't just look far away. Webb looks into the past. Distance is a timeline. The end of the lens is not the finish line. The end of distance is the starting point. The next photon is already on its way. If you enjoyed this journey to the dark side, like the video to let the algorithm know. There's still so much Webb hasn't explained. Paradoxes waiting to be unraveled. Because next time, we will sail where dark matter cannot reach. Exploring edges where even gravity fails. What is hidden there? Maybe the final layer of the universe's truth.